Welcome, beloved sibling. It is I, Aaron Freeman, not a scientist, but a sciencey optimist here with a real, live, grown-up, not just a scientist, but a physicist, that most rigorous and unrelenting of sciences. Dr. Nicolas, the world's greatest living physicist, Gross, lecturer in physics at Boston University, and our buddy every Friday for Physics Friday on Science the Day.
Excellent.
Good to see you, my brother.
Just don't say the rigorous part to mathematicians; they would be.
But you guys, you physicists are all rigorous about you're obsessed with your math. What are you talking about? There's whole branches of physics. It reminds me of one of my favorite physics quotes. Yeah. Was Barry Gell-Mann, who said, "Quarks exist. The fact that experimentalists have not found it is not my problem." Anyway, but have you heard that quote?
Yes, I have heard that quote. It always bothered me a little bit because it's an empirical science. Physics is an empirical science, right?
Yeah.
Right, and so it's really the only science where we really separate the theoreticians from I've harped on this before, but separating the theoreticians from the experimentalists, and they're like, you can't do both. You got to pick one or the other, and then there's like these little warring clans, that
well, that is true. But let me say, have I got something wrong here? But I thought that, like, for example, quantum mechanics is a whole quantum physics that we talked about is just basically a bunch of math.
Well, up until the point where you make a prediction and then somebody's got to go do the experiment.
Well, yeah, but look, I mean, like, for example, yes, but how much quantum experimentation? Well, anyway, let's not do that right now because we are here to talk about something even.
We can talk about something that also is mathematical.
Also is mathematical and also as weird as the quantum world.
Also has not only experimental evidence, but practical evidence for it.
Then that's true. Well, of course. Well, first of all, let's say hi, Constance. Welcome. Delighted to see you here. But of course, one of the
honey, good to see you.
Oh, so one of the big things we're going to be talking about is one of the most boring common forces in nature. Right? I mean, this is so boring.
It's boring unless you're Newton or Einstein. And then
well, yes, I'm just saying that we all experience gravity endlessly.
And it was hard for even for Aristotle to wrap his brain around the fact that gravity isn't just there, right? It's not that there's something that, and so Aristotle was trying to explain falling objects, and then you've got to think about, well, it's not just it doesn't just happen. There's some way I can model it and reason my way through it. So,
and it turns out that gravity does some really bizarre things. Last week we were talking about the quantum realm, and you suggested we chatted this week about a movie that I had seen a while ago but hadn't seen until recently, until last week after our conversation, and that is Interstellar.
Oh, so you've done your homework.
My goal. One of my goals here, Nick, is to get through one of these chats with you and not say something that's clearly, absolutely, unequivocally wrong. Okay?
Okay.
Now, I've looked back at the video. I've never done it, okay? I always say something that is absolutely, unequivocally, indisputably wrong. So at least I know which movie we saw. And but I actually think that I have some clue about this weird phenomenon that we're talking about.
Okay.
So the weird thing one of the weird things that we in that movie that is, it was hard for me to understand is they land on a planet that is near a black hole. Is it a black hole? Gargantua. And
yes.
I'm sorry.
Yeah.
And it has this very strong gravitational field on this planet. And so they go down to the planet, and 1 hour for them on this strong with the planet with a strong gravitational field is the equivalent of 7 years back up in the ship where it's floating around, where the ship is orbiting the planet. And that is weird. And that's because of gravity, that gravity will make time move more slowly. What the hell is that?
So that's, there's both a, what's interesting about that is there's both a, there's two different things going on, right? And so this has to do with relativity and the warping of space and time. So in sort of classical physics and our everyday world, you can like go map out like, you know, fields, right? You go map out literally map out a grid system, like set up a coordinate system. Like New York City, right? You can set up a coordinate system, and they set it up so that I forget exactly how long. You've got small blocks and big blocks, but the distance between the avenues is the same, and the distance between the streets is the same.
Laid out on the grid, more or less.
And whether you're up in the Bronx or you're down in Battery Park, the distance, if I have to walk from one street to another, I cover the same distance.
Yes.
Right. So I've got this nice grid system set up, and that's a very Newtonian, Cartesian, Enlightenment, 18th, 19th century, you know, Victorian England approach. So we've got things measured, we've got them organized, we've got them like, and I can put a stopwatch on it, and I can time the cabbies as they go by from one block to the other, right? And the lights are all timed, and like, so like New York City is a perfect example of this. Like, there's timing for the lights, there's distances for the things. Everything's mapped out. And so
you can describe your position anywhere in Manhattan with two numbers.
Right. Exactly. Okay. And that's true.
Oh no! Don't tell me I said something wrong already.
No. You haven't said anything wrong already. I'm just trying to make I'm trying to use what you're saying. I'm trying to make. I'm improvising. I'm trying to use the gift you gave me.
Well, I'm not wrong yet. I'm not wrong yet.
No, you're not wrong yet. So, and that's true for even in special relativity, except that I have to tell you who measured the two numbers. So you could have the local bus going by at its like 15 miles an hour, and you could have the cabbies going by at 60 miles an hour, right? And the strange thing about relativity is the measurement of their times are different, and the measurement of their spaces are different. So, and so you get this thing called length contraction. So the cabbie, so I can be standing on the corner of Fifth Avenue and 32nd Street, and I can watch a bus go by, and I can watch a cab go by, and if they both had a ruler, right, a meter stick, I would see that the cab's meter stick is just a little bit shorter than the one on the bus.
Wait, time for a graphic. Time for a graphic now?
Yeah, time for a graphic, yes, right, excellent. Right.
See what we got here?
Yeah, so this all has to do with the constancy of the speed of light, the fact that the speed of light is the same in all reference frames. So what we all do agree on is that the speed of light travels at about 300,000 million meters per second.
300,000 kilometers per second.
300,000 kilometers per second. Yes, right. Good. And
or 186,000 miles per hour for those of us in America who are not a part of the rest of the world.
And so what's strange about that is I could be traveling, so you could be standing still, and I could be traveling at, say, half the speed of light. And we would both see, and you would fire a light beam, and I would still see it traveling at the speed of light.
Whereas if we were traveling in the same direction in two different trains or two different cars, I would see your car as traveling its speed minus my speed.
Right. So that's Galilean relativity, and that's good at low speeds.
But we would both see, regardless of how fast the individual critter, the machines were going, our cars, our trains, we'd both see light traveling at the same speed, even though we saw each other traveling at different speeds.
Right.
Okay.
Yes. Okay.
So explain.
And,
but I'm still waiting to understand. Tell me about why it is that gravity slows down time.
So because of the speed of light does this thing that's kind of magic, right? So I can be traveling at half the speed of light, fire a laser beam, and you can be relative. So I can be traveling at half the speed of light relative to you, fire a laser beam, and we'll both see it.
Right.
You won't see it as traveling as 1.5 times the speed of light. You'll see it as traveling at the speed of light. Right. Then there's two effects to that. One is length contraction. So I see things as you get closer and closer to the speed of light, you see objects as being shorter and shorter.
Now, you mean as I'm traveling closer to the speed of light, the objects around me I see as shorter and shorter, or anyone observing me?
As far as you're concerned, you're standing still, and they're all going past you at the speed of light. Then you see them as shorter.
Okay. Little mini critters.
Yeah, little mini critters, and so this nice Ferrari suddenly looks like a VW Bug.
Right, got it.
Right. Okay. But then the second thing is, if you go to the second diagram, the one that's time dilation.
Yeah.
Okay, so now this one, it looks at, so the white line is a light beam.
Right. So on the left, there's a light beam that's traveling between two mirrors, looks like.
Two mirrors in the spaceship. So this is two different observers. So the guy on the left is in his spaceship. And again, as far as he's concerned, he's just sitting still in his spaceship. Right. He can't tell any difference, right? And so he watches the light.
I am in my car. Just like when I'm in my car, I'm sitting still.
Well, even though, so more like in a train, when you can't, that thing where you can't tell which train is moving when you're in the train because you don't feel your motion.
Well, that's New York subway. Yes,
right. So even though you might be moving relative to the platform, you can't tell what's moving, right? So this guy feels like he's sitting still, and he watches a light beam just bounce back and forth between the two mirrors. But his friend on the ground is watching him go by, and as far as she sees, that light beam travels the full. It not only travels up and back down, but it also travels along with the spaceship.
Right.
Because they have to agree that the light beam bangs against the mirrors.
Right.
That's an important tenet of special relativity and general relativity, is that events are the things that are fixed. So they have to agree that the event of colliding with the mirror, the physical event of colliding with the mirror, is the same.
So this particular little illustration you have here, this really is special relativity, right?
This is special relativity, yeah.
Right. And special relativity has only to do with the speed of light. Or primarily to do with the speed of light. I was wrong already. I said only. No, it's not only. It's primarily.
Well, no. I think you're. So no, you're right. You're right.
Oh,
you're right.
Oh, okay. How is that?
That was good. So you notice that that light beam then had to travel a longer distance, right? But it travels that longer distance at the same speed for both for the woman,
right?
And so she would see this for this guy. If it takes a second to go up, she would see it take longer than a second because it has to travel a longer distance.
Okay, this makes sense. Okay.
And so as far as she's concerned, it's like maybe 2 seconds have gone by. And so she sees his clock as running slow.
Okay. All right. His clock is running slow because it's taking longer for the light to go back and forth between the mirror from her perspective than it does from his.
Yes,
Okay.
right. And so that's time dilation. So that's the way in special relativity you can warp space and warp time. Okay.
You get for a given observer time, and this is what we're talking about in Interstellar. From the point of, well, it seems to me it's worth mentioning that relativity really just means that things are different depending on where you look at them. When you look at them, that's really like the core of relativity, is that your and my perspectives will show us different worlds, or the
Right.
phenomena of the world will seem different depending on where you're sitting.
Right. Well, so in the
Relative to
particular measure thing, we measure the distance between things and the time between events as being different.
Right.
So again, we have to agree on the events. Otherwise, if we don't agree on the events, then our realities diverge, right? And that doesn't make any sense.
Right.
Right.
Except in the Marvel comic universe, but never mind. You have the reality stone, but we're not talking about that.
Okay, right.
Okay. So now we can see, we can observe light, the path of light, and the time it takes from a light to get one place to another at traveling at different speeds depending on whether we are in motion or watching the light in motion.
Right.
Okay.
Yes. Right.
So now, how is it that being near a strong gravitational, because in what I say in my little video introing this, that my time travels more slowly at my tootsies,
right,
little feetsies, than it does at my balding head.
Right.
It's like only a little tiny bit, but is that true? Is the time traveling more slowly?
In principle, yes. Right. So your feet are just a little bit younger than your head. Well, I just was looking at. I'm looking at my other screen over here. I was just looking at something, and I have to. But yes, in print. Let's go with that for now.
Yeah, I mean it's a very small, but it's all similar. But the reason that, and why is in theory why are my feet younger?
So once Einstein puts all of special relativity together in 1905, but then he's bothered by something, and what he's bothered by is, let's suppose you're in an elevator or a rocket ship.
Okay, I like that.
So the thing that you can't tell if you're just sitting there, right, in your elevator, is you can't see outside. So you could be sitting there feeling gravity, feeling the acceleration due to gravity. You can drop a ball and it'll fall at 9.8 meters per second squared.
Right.
Or you could be sitting, and that's because you're sitting on a big massive object.
Yeah.
Or you could be in space and your elevator or your rocket ship is accelerating.
Got it.
At 9.8 meters per second.
Right.
And so you imagine then dropping that ball again and you see it fall. Right? Because you drop the ball, there's no force acting on it. You're being pushed by the elevator or the rocket ship, but the ball, there's no force acting on it. It's just sitting there, and you're accelerating past it until it hits the floor.
Ah, okay, all right. But you can't tell.
But you can't tell.
Okay.
Right? You can't tell just from that experiment.
Okay.
And so Einstein's revelation then was that, hey, these two are equivalent, and all of the pieces of special relativity start to come into play. So again, as you accelerate, you're now warping space and time, but if you're accelerating, you're warping space and time, then the gravitational fields must also warp space and time.
Say that again.
So if I'm accelerating, I'm changing my speed. If I'm changing my speed, then I'm going faster and faster, and I start to warp. I start to have length contraction and time dilation. My rulers get smaller and my clock runs slow.
So let me just say also, right? Everything warps space. All matter warps space-time.
So Right, and so I'm trying to connect up the special relativity to the general relativity.
Okay.
So
Making sure.
So if I was just accelerating,
Right.
it would look like special relativity with some little bit of add-ons. But now I'm sitting here on Earth, and it also feels like I'm in an accelerated space. And so that must also warp space and time.
Okay. Because the fact that I feel it is an indication that space-time is being warped.
Yes.
Because the warping, the effect of warping space-time is upon my experience of my own weight mass.
Your observation.
Right. So now as I was talking to a friend of mine, as I mentioned this to you, I was talking to a very sciencey friend of mine, who's a very interesting guy, who's a probabilistic statistician at Stanford. I was asking him, how does this work? How can it be? And his answer was, which is interesting, and you mentioned it, that gravity itself provides the acceleration that causes, because we know that the closer tell us quickly Einstein's famous twin experiment about
I don't think Einstein came up with this. I think it was Minkowski, but I'm not sure. I'd have to go look up the history. But the idea, so this is a special relativistic effect. So you send a twin out, and so you have two twins, right? And one stays home on Earth and has a nice life, and the other one you send out off at half the speed of light.
Right.
And there's a little bit of a paradox here, but then you turn him around and bring him back.
Right.
And the issue is that they're both traveling relative to each other. So you would say that each of them sees the other one's clock run slow. So one of the twins should age more slowly than the other.
The one who's traveling near the speed of light.
Well, so if he just goes out and is traveling at the speed of light, or half the speed of light, let's say, right? Then what you don't know, or what what relativity says, is him going out traveling at half the speed of light, and him looking at his rocket ship, watching Earth recede at half the speed of light, look the same.
Right.
So
just like the trains in New York.
Right. So part of the twin paradox is, well, who's right? Right? Who's got the slow clock? Because they both see each other's clock as running slow.
Well, although haven't there been experiments that have gone on, like were done like in the 50s, with two clocks synchronized here on Earth? One clock gets into a plane and travels at whatever it is, 600 miles an hour, and the one that is traveling will click more slowly than the one that is on Earth.
Yes.
So that's because of its speed at which it's traveling.
Right. And so that's all. And so that's all been proven. I mean, the solution to the twin paradox is you actually need three twins, because one of them, you got to have somebody coming in. It's a reference frame change, and I guess it's a exercise for an undergraduate physics major to sort this out. But indeed, the observation of the moving, we can see things that move relative to us as running slow, their clocks running slow. And
so my friend Sam said that one way to look at it is that the reason time moves more slowly as you are near a gravitational force like the Earth, like the gravitational center of the Earth, is that gravity itself provides that acceleration. The closer you get to the gravitational center, the more strongly is the force of gravity, and that accelerates you such that time, just like the twin who's moving, time stretches out, time moves more slowly. But a more elegant and much weirder solution is,
well, pull up the third diagram that we have, the one that the funky grid.
Let's see here. Yes,
that one. Yeah. Okay, so here's so let's take our New York City grid system, right? And somewhere around Midtown, we drop a huge mass.
Yep.
Okay. And it distorts the grid system in Midtown, right? And
Obviously,
so
it's a
now,
very well built system that can survive that. It won't just crack
yes,
it.
right.
That's right. It stretches.
Yes. But it stretches, right? It stretches the grid system.
Right.
So that now the measurement, the initial. So if I'm trying to use my pointer here, but you can't see that. If you see the little curvature in the middle there,
Yes.
The measuring sticks start to stretch and bend and distort. And similarly, so I'm going to make an analogy here. Similarly, the clocks are going to start to stretch and bend and distort.
The blocks
due to
in Manhattan, the blocks will become longer.
Right.
Right. And then since space and time are one fabric, the time and when the space becomes longer, the time becomes longer. When the space gets warped, the time gets warped.
Right.
And that is why it is that things that this is an example, an illustration of why time moves more slowly in the under the influence of a strong gravitational force, because that ball that we just imagined that we dropped onto this grid, that is that strong gravitational force that warps the grid, stretches things out, just like when our twin stretches out, when the acceleration stretches out space-time.
Right. Yes. So if you're sitting down in this well, you're going to see time run more slowly because it's going to be stretched and distorted. So you're going to let me rephrase that. If you're observing somebody down in this well, you're going to see their clock running more slowly.
Now,
so time will pass more slowly for them. They will age more slowly. You will age faster. You'll be sitting there eating your protein bars for 7 years while they're like having a nice, lunch, one nice picnic lunch on the surface of this planet.
Okay, but in real life, this gets really weird in the International Space Station, because in the International Space Station, it is further from the Earth's gravitational center, so time should move more swiftly relative to the Earth.
Yep.
But it is traveling at, 17,000 miles an hour, so that time moves more slowly.
Right.
Why? That's not fair.
So you've got to compete. You've got two competing effects. Yeah. So it's not one answer. It's two competing effects that are going on. Yeah. And so what you've got to figure out is actually go back to that that plot. Oh, can you go back one?
Oh, sure.
We'll come back to this in a minute. Yeah, so what you've got to figure out is what's your path are you taking around, so you can imagine the International Space Station as orbiting around the center at some distance in this well.
From that gravitational force.
From that gravitational center, right? And then you've got it. So it has some time dilation due to the distortion of space-time. But then it also has some time dilation due to its motion.
Okay.
And if you're comparing it to somebody who's standing not quite still, because we're also twirling around, right? But somebody who's on the surface of the Earth, so deeper in the well, then you've got to see what the difference is and whether the two competing effects work out. And I was just I didn't know, I had to check some things before I got online with you, and I didn't know this, but
yeah. As physics formulas go. Well, we have just lost. Oh, here he is. He's back. But that was just a quick little interlude. But our good buddy, the world's greatest living physicist, is right back, and there he is.
Yep, you're right. we got time distorted.
The GPS somehow or other. That's right. Anyway, you were saying.
So yeah, I had to double check something, and they've got there's a nice Wikipedia page on it. On gravitational time dilation.
Yes, there is. Yes.
And so the GPS satellites, the clocks. So can we do a diversion into how GPS works?
Well, yeah. I mean, sure. Yes.
So the GPS spacecraft are basically they're sophisticated flying clocks.
Okay.
So you can get your time from GPS if you wanted to, because that's all they're sending you is time. There's nothing else clever about what they do, other than whatever's power. I mean, they've got to do power of the spacecraft and do orbital corrections every so often. But their primary instrument is a clock.
Okay.
And
their clocks would, because of their speed, would run more slowly than would my phone here, because this clock effect is the same for whatever kind of clock you're using.
Whatever kind of clock you're using. In fact, it's the same for biological processes. It's the same for physical processes. Any kind of processes are going to run well. If the time dilation is to say that they would run more slowly, then yes, they'll run more slowly.
Right.
In the case of the GPS orbits, because they're further out of the gravitational well,
okay,
the gravity time dilation change that our clock sees relative to their clock is bigger than the special relativity time dilation. And so the GPS clocks actually run a little faster.
Okay, all right. And so
because as you pointed out, there are these two competing effects.
Right. And so the GPS clocks are calibrated to make up for the differences in time, in the passage of time,
right,
based both on their distance from the gravitational center of the Earth and their speed relative to the ground.
Right.
So they have to do that.
Right.
And that's
so they would lose.
I mean, that's a real life.
Yes.
That's this
weird,
bizarre space-time.
They have to reprogram these so that they make up something like I think in a day. I forget what the time, but it was a surprising amount to me. They were talking about microseconds, which if you're trying to figure out how long the radio signal from the GPS, and that's how GPS works, is to get your position, where that spacecraft is, and how long it took for the signal to get to you because of the time it sent you.
Right.
Right. Yeah.
With triangulation.
So you do triangulation, but I know if we say the closest satellite, I'll get a timestamp from it, right? I'll just get a time from it, and I compare. And my phone compares that to, well, if it's GPS enabled, your phone compares that to its current timestamp and says, aha, that radio signal had to travel this far for those timestamps to be different. But if you're off by microseconds, since you're talking about the speed of light, that could be a big distance. That could be meters or maybe even kilometers.
Yet it works. As weird and bizarre and strange and counterintuitive, this notion that time is different depending on how far you are from the ground and how fast you're moving, which just makes no sense at all. It shouldn't be right. Time ought to be freaking time. But despite that, it's not. And it's not only, it's not like the quantum world, but because we all have our GPSs. Like this is
Right.
something that's just normal. With this normal thing that we do every day. We live in this weird. We live with machinery that copes with this bizarre time dilation, space-time dilation, and the warping of space-time.
And some of that machinery also uses the quantum realm to figure things out too.
What do you mean?
Well, we should have talked about this last week. This is a quantum device, right? It's got transistors in it. It's got semiconductor transistors in it that use quantum mechanics to do their job, right? So I've got both special relativity, general relativity, and quantum mechanics in my hand.
And you have got it all in that great big old Dr. Nicolas Gross, the world's greatest living physicist brain. It's all up in there. It's like vision. It's all there, densely packed in that gray matter.
We've got comments.
Yes, well, the Constance said that you had vanished for a second there, and Constance was a little worried about you, but now you are back. And now we are out of time. But
I think so. Yes.
But thank you so much. See, now I didn't say anything egregiously wrong today.
I don't think so.
I may go back and look at this and see that I really did. But as far as you know, I didn't say anything egregiously stupid yet. So I am talking to my good buddy, Dr. Nick Gross.
Nothing you say is stupid, Aaron.
Okay. It's often incorrect, but not necessarily. Right. Okay. It's incorrect in a non-stupid way. But Dr. Gross is here with us.
I went too fast.
What? You see there? Now, I heard there's an Einstein quote about that I heard. That if you are sitting on a hot stove, a second seems like an hour. If you're sitting with a beautiful woman, an hour seems like a second. Have you ever heard that one?
I haven't heard that one. But
well, I have no reason to believe that Einstein actually said it, but I've heard it attributed.
I'll take your word for it.
I can absolutely tell you that I am 100% positive that I think I remember hearing it at some point long ago. So that's solid. Okay, I am right there.
You're right there. Excellent.
All right, Dr. Nick Gross joins us on Physics Friday. We hope we'll get a chance to talk to you next week, brother. We'll figure out something fun something fun for the gang. Constance, thank you so much. Time went too fast for you too, for us being with you. We're delighted to spend time with you. Thank you all for watching now. Thank you for watching later. Appreciate all the folks who watched last week's video. It was our most watched videos ever. Hopefully this will be even better. Dr. Gross, love you very much, my brother. Have a great weekend.
All right.
See you soon.
Bye, everybody.
Bye.